Hello chemists, this is Ms. Placino and you're watching lesson 4.2 on ionic bonding. In today's lesson we're going to talk about what ionic bonds are, as well as how we're going to represent ionic compounds using Lewis structures. So some goals for today's lesson: define what an ionic bond is and predict when one will form. We're going to be able to predict the formula of simple ionic compounds, and we'll be able to represent ionic compounds using Lewis structures. All right, so let's get into the lesson. Ionic bonds occur between metals and nonmetals. So when we take an element from the right side of the staircase, we combine it with an element on the left side of the staircase, we end up with something that is primarily ionic in nature. This occurs because we have a transfer of electrons. We know that metals tend to lose electrons and become cations, and nonmetals tend to gain electrons to become anions. So really what happens is just one of the electrons, like in the outermost shell of the metal, is going to get transferred to the outermost shell of the nonmetal. That's going to lead to a positive and negatively charged ion. And we know that opposite charges attract. So they're really just held together by this electrostatic attraction. And that is what a compound, an ionic compound, is going to be. Ionic compounds exist as crystal lattices, which are really just 3D networks of cations and anions that are mutually attracted to one another. So you usually end up with these like big repeating structures of positively charged and negatively charged ions. They're very highly organized, and you can see that it's just alternating, in this case, sodium plus ions and chloride with a minus charge ions. We would never try to write all of this out as far as like a formula to try to account for every single ion. Like I wouldn't have to count 1, 2, 3, 4, 5, so on and so forth. Chlorides do the same thing with the sodiums and end up with huge subscripts. Instead, we use formula units, which just tell us the ratio of atoms, or I guess more technically ions, in the crystal lattice in the simplest form. So this is sodium chloride. You probably knew this formula before you came to my class, NaCl. Obviously, there are more than one sodium and one chloride ion present in this crystal lattice, but they're in a 1-to-1 ratio. So instead of trying to represent all of the sodium and all of the chloride ions, we just put them in the simplest ratio possible. Yep. All right, so one big thing that we need to be able to do by the end of this lesson is to predict the ionic formula units. So I'm going to walk through a couple of steps and we'll talk about how to streamline it. But first, let's start with this Bohr model of the atom. What element is represented? Well, hopefully you see the 12 protons in the nucleus. You go to the reference table, specifically the periodic table, and we know magnesium is the only element on the table with 12 protons in its nucleus. Will magnesium gain or lose electrons? Well, magnesium is a metal. It's over on the left side of the periodic table, and we know that metals tend to lose electrons. How many electrons does magnesium want to lose? Well, if you look at its valence shell, its outermost energy level, you've got 2 electrons. 1, 2. In order to complete its octet and to end up with 8 electrons in the valence shell, magnesium is going to try to get rid of both of them. Repeat that same process for this Bohr model of an atom. All right, hopefully 17 protons. We're looking at atomic number 17. That's chlorine. Chlorine over on the right side of the staircase, group 17, it's going to gain electrons. As far as how many it wants to gain, we know that main group elements, S and P block elements, are trying to get 8 electrons in their valence shell. I see 7. So chlorine will want to gain 1 electron. Okay, hopefully so far so good, and you understand how we got the element identities. We know whether it's going to gain or lose based on being a metal or a nonmetal. And as far as how many will be lost or gained, if we look at the valence shell of our atom, we know we have to get to 8. So we're going to be able to lose 2 from magnesium and gain 1 for chlorine. All right. Magnesium has to lose both of those electrons. Becoming magnesium with just 1 valence electron doesn't really make it stable. Is magnesium able to transfer both of its electrons to the chlorine atom? Hopefully you're thinking no. Chlorine really only has room to get one more electron, so I can't give both of those to chlorine. I'm going to need a second chlorine atom. What's going to happen is an electron from magnesium will get transferred to one of the chlorine atoms, making it an Mg plus and then a Cl minus. And that second electron will get transferred over to the other chlorine atom. Now I've got Mg, 2 plus, I have a Cl minus, and another Cl minus. So my formula unit must be MgCl2. And that is representative of 1 magnesium, technically magnesium ion, and 2 chloride ions. I've got to balance out those charges. So +2 minus 1 equals 0. When you try to predict the formula unit of an ionic compound, you don't have to go through what we just did with drawing Bohr models of the atom and trying to physically transfer the electrons. There's another technique that we use called the crisscross method. So I want to talk about this and then we'll get to try it out. First thing we need to do is write the ions for each atom. So in this case, we were working with Mg and Cl. Mg is a group 2 metal. It has 2 valence electrons. We know that it's going to try to lose both of those electrons to give us an ion with a charge of +2. Chlorine is a group 17 nonmetal. It's a halogen. It's going to gain an electron to have a charge of -1. It's called the crisscross method because the charge of the cation becomes the subscript of the anion, and vice versa. The charge of the anion becomes the subscript of the cation. We don't take the plus and minus with us, but we do take the number. So just to show you, we'd take that 2, crisscross it over to the Cl. We'll take that 1, crisscross it over to the Mg. This is telling us the ratio of magnesium to chloride ions. We're going to reduce the subscripts to the simplest terms. Well, it doesn't get any, I can't reduce this down any further. 1 to 2. I can't have a 0.5 to 1. I can't have half of a magnesium ion. So this is already in simplest terms. And then I just push them together. We drop the subscript of 1. If there's no subscript present, it is implied that you just have a single atom or ion. And that's it. The crisscross method is extremely useful, and we will be using it a lot this semester. Okay, so I'm into the practice problems right now, and I want to look at a couple of these and trying to predict a formula unit. So I'm going to look at this one, and we'll do Ba and O. All right, so here you're not told what the actual charge of the ion is, but I bet you can figure it out. If you find K, potassium, and Br, bromine, on the periodic table, you should be able to determine how many electrons each of them needs to lose or gain to complete their octet. Potassium is a group 1 metal. All alkali metals will lose 1 electron to have a charge of +1. Bromine is a halogen in group 17. It's got 7 valence electrons. Halogens will always gain 1 electron to be just a -1 ion. So if I take the +1 and -1 and I crisscross them, I come up with Kbr as a formula unit. See if you can predict the ions for Al and F. Aluminum is going to lose its 3 valence electrons to be Al3+. Fluorine, it's a halogen, so it's going to gain an electron to become F-. Crisscross method. I'll have Al, F3. This makes sense. I need 3 of those -1 ions to balance out the 1 +3. Good. And let's wrap up with Ba and O, barium and oxygen. Barium, alkaline earth metal. it'll become A plus 2. Oxygen, group 16, with the 6 valence electrons, it'll gain 2 to have a minus 2 charge. By convention, we always put the metal or the cation first. I'll use the crisscross method. I'll do Ba2O2. Remember, we've got to reduce our subscripts down to lowest terms, so Ba2O2 is technically not correct. I'm just going to turn this in to BaO. And that's it. Definitely something worth practicing with. We'll be using this, like I said, throughout the semester. Let's get back to the notes. Actually, I think I'd probably just prefer to take care of it here, so we'll do it here. So we're going to draw a Lewis dot diagram for an ionic compound, and we'll stick with this MgCl2 that we've been working with so far. The first order of business is to draw the Lewis dot diagram for each ion. Not atom, but each ion, since in an ionic compound, ions are present. We talked about this in the previous lesson, how your cation is always going to have no electrons around it. And your anion is going to have a complete octet. So there are ions. I'm going to draw brackets around each ion. I'm going to keep the charge of the ion outside of the brackets. You can see we did that here. The 2 plus and the minus charge, they're outside of those square brackets. And we can use subscripts or coefficients to show the number of each ion present. So I can go ahead and put a subscript of 2 if I'd like to represent that there are 2 chloride ions. When we say coefficients, I can actually put that in front, not subscripted of the chloride ion. Sometimes you might see examples where a second chloride ion is drawn on the other side of magnesium. All of those are perfectly valid. Let's look at drawing a couple for the formula units that we predicted to wrap this up. They're all going to take on a very similar format. You should have your cation, your metal, with no electrons around it, square brackets, charge outside of the bracket. Your nonmetal, the anion, is always going to complete its octet. So you should have a full valence shell, 8 electrons around the anion, keep the charge outside of the bracket. That's it for potassium bromide. We'll do one more just to wrap up. Aluminum fluoride. Am I done? Well, the ions themselves looks good, but I'm not finished. I need to make sure that I show that I need 3 of those fluoride ions. I'm going to use the subscripts. That's it. Hopefully you've noticed the pattern that's kind of showing up just looking at the 3 examples that we've done. The format is the same again and again and again, really, for your ionic compounds. I've got a bunch of them there to practice with, so I'd really encourage you to do so. Thanks for tuning in, and I hope you found this helpful.